So now let's take a look at question 1, and we can go through the explanation. So go ahead and read that to yourself, and then when you're ready, we can go through together what the explanation is.
So it's asking, so when the wave is going through the material, was it Huygens principle? How it's still like how it's applying through the material?
Right? What we need to explain is, why is it that we can think that every point on the wavefront, why can we imagine every point on the wavefront to be a new point source? Why can we imagine every point on the wavefront to be a new point source? And this is kind of the explanation right here. Notice that here we have this wave, and where the wave is, it's creating a new oscillation, and then we saw how this was a new source of EM waves. So this little oscillation here can be considered a new source of the waves. So let me expand the picture here. It's easiest to think, see. So let's say we have kind of a plane wave coming in. So here we have a plane wave coming in. So here's a whole bunch of parallel beams of light. Well, let's just redraw the whole thing.
When it's oscillating, does it give off a spherical?
Yes. Okay, so let's say we have a plane wave that's moving through glass. I'm not going to draw the glass, let's just say that the whole blackboard is the glass. So we can see the plane wave would move like this. Here's like what it would look like before, say, and here's what it would look like afterwards. So let's just look at one wavefront. Now let's think about this point on the wavefront. What is happening at this point on the wavefront? Well, we know at this point there is an oscillating electric field. That's what the wave is. It's an oscillating electric field. And we know that that is going to cause any molecular dipoles at this point to oscillate. But of course, the molecular dipole is tiny, right? Remember that we were talking before about what causes spherical waves point sources. Like, it's like if you drop a little, say, a little rock in a pond, you'll see spherical waves coming out from it. If you dropped a log in a pond, you wouldn't see a spherical wave, right? You would see cylindrical, because the log is not a point. It's only if you drop something small, like a point, that you get the spherical wave. Well, the molecular dipole is very small, so we can treat it like a point source. Well, if it's treated like a point source, we would expect that its oscillations are going to give us a spherical wave. So the logic is, this wavefront consists of an oscillating electric field, so whatever molecular dipole here is going to oscillate, and then that oscillation is going to give us accelerated charges. But we know that accelerated charges are themselves a source of an electromagnetic wave. Okay. So when we get those accelerated charges, this becomes a source, and then that's going to give us a spherical wave coming from this point. But what about this point on the wave? Well, there's a molecular dipole here too. There's a molecular dipole here too. So this molecular dipole is also going to start accelerating. And that is also going to be a new source of an EM wave. And then there's a dipole over here, and it's going to be accelerating, and that will give us a new source of a spherical wave. So we really have explained, so again, Huygens' principle is that you can treat every point on the wavefront as the point source for a new wave. And the way we can explain that in a material medium is, well, at pretty much every point, there's going to be an oscillating molecular dipole. At pretty much every point on the wavefront, there's going to be an oscillating molecular dipole, and those are the actual physical sources of these new little wavelets. So before, when we were talking about Huygens' principle, we just said that every point on the wavefront is going to be a point source for a wavelet, but we didn't say why it's going to be the point source for a wavelet. Well, the reason is that every point in the wavefront is a molecular dipole that's going to be oscillating, and that gives it, and that would mean accelerated charges at that point. Well, any point that there's accelerated charges at, we know that's the source of a spherical. We know that's going to be the source of a wave. You asked a good question a second ago, whether the oscillating dipole would really give you a spherical wave. That was a good question, because I told you before that the EM wave doesn't propagate in all directions from the oscillating dipole. It only propagates perpendicular to the oscillation. So it seems like that would not give you a spherical wave. I think the answer to that, though, is any particular dipole might, any one dipole might only be propagating in one direction, but actually at this point there's a whole bunch of dipoles, and they're all oriented in different directions. Right? All the so at any one point here really is a whole bunch of molecular dipoles that are oriented in different directions that would be oscillating in different directions. So I think that explains why you would still get a spherical wavefront. I don't know if I'm thinking clearly through that or not. That was a good question. But anyway, the basic point that we're trying to explain is, why does Huygens say that you can treat every point on the wave as a new point source? Well, the reason is that at every point in the wave, there's going to be that oscillating dipole that gives you the accelerated charges, and we know that accelerated charges are the source of an EM wave. All right, so the problem was to give a atomistic explanation of why the points on the wavelength are the wavelets, and I think that's what we tried to do. Does that explanation make sense? Okay, so let's see. What did he say? The wave shapes the material. In the case of the wave, that may drive an electric dipole, or vibrations, or electrons. So he's not talking not just dipoles, but he's talking about some type of charge is going to be oscillated there. Some type of charge is going to be oscillated.
You say that the wave induces a dipole?
He says that...
drive an electric dipole.
Yeah, he drives the dipole, but what does it drive it into? He says it drives the dipole into oscillatory motion. That's the key. It drives the dipole, or some other type of charges. It drives some type of charge into oscillatory motion. Well, oscillations have acceleration, as we were saying, and acceleration is the source of EM waves. So those are the secondary dipoles over here. So point on the wavefront has a oscillating electric field, so that leads to oscillation of a atomic or molecular dipole. But we know that anytime an electric dipole is oscillating, that is a source of EM waves. Well, that explains Huygens' principle. Then we get, at that point, so we've just shown that that point is a source of EM waves. I guess I should put in the extra step. The oscillation of the dipole means acceleration of charge. And acceleration of charge means that that is a source. I think you generally will tend to get more credit for explanations if you lay it out kind of with arrows, step by step. So what did Huygens' principle say? Huygens' principle says every point on the wavefront is a source of an EM wave. So Huygens' principle is this and this. Every point in the wavefront is a source of an EM wave, and the problem is asking you to fill in these intermediate steps. Why is the point on the wavefront a source of EM waves? Well, the point on the wavefront has an oscillating electric field, which oscillates a dipole, and we know that oscillating dipoles are accelerated charges, so that's a source of an EM wave. Okay.
Makes good sense.
These, so it seems like your instructor really likes these. He definitely likes to put in these kind of thought and conceptual questions. These take the longest to explain. Yeah. Okay. And the problem is, of course, you won't see this exact question on the test, so we tried to cover the whole general subject here so that you have something intelligent to say when he makes a variation on this. Okay. All right, is that good enough for that? Yeah. All right, so let's go on then to part B.
Just this little paragraph takes so much understanding.
Yeah.